Question 6. This seems to be more on introductory organic chemistry. They're talking about, well, draw the skeletal. That's the first thing you can think about in the question. They want skeletal, finally. And they say C8H10, they want structural isomers. So they're not looking for stereo, they're just looking for structural isomers. So you should have circle or underlined part of this thing, which they want you to do. There's also given information on carbon-13 NMR. So you're looking for how many different carbon are there. So we need to think about symmetry and number of carbon environments. How many carbon environments are there? So let's get started. C8H10, so all of them have benzene ring. Benzene ring is C6H6, but when they are substituted with something, they're going to be C6H5 when it gets substituted. My question now is C8H10. Could it be just like this? 6, 7, 8, 9, 10. So there will be C6H5 from the benzene ring, 6 carbon, 7, 8, 9, 10. So there's C10H, there's 5 hydrogen because one of it is substituted, 5 hydrogen, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there's C10H14. I want C8. I beg your pardon, I want C8. So I need lesser carbon, 6 carbon, 7 and 8. So there should be C8H 5 hydrogens, 6, 7, 8, 9, 10. So I'm just looking for things like that. There is already one skeletal formula. So I don't know which order round it is yet, but let me try and draw all the possible isomers first. So I could have one carbon there and one carbon on the other position. I could also have what am I doing? I can just copy paste that because I'm working on screens. Very nice and easy working on screens, not so nice and easy for you, of course. Then what we do is we just put the methyl group somewhere else. I don't put it there because putting it there is the same as 1, 2, 3. So it's a 1, 3, which is the same as that. This is a 1, 3 position. It's a 1, 3 dimethyl benzene. And the other one is a 1, 4 dimethyl benzene. This is a 1, 2 dimethyl benzene. This is just what you call ethyl benzene. Okay, all of them are C8H10 obviously. So don't want to spend too much time on the name itself. Maybe not. Okay, let me just copy paste that and get the name right. Obviously there's not the right name yet. So there's 1, 1, 2, and this is 1, 4. Perhaps I can move it a little bit there to make myself some more space. Okay, so let's partition this so that it looks a bit clearer. Alright, so now having looked at these, we need to try and think about the number of carbon environments that are different. So here you can hopefully see there is a symmetry there. So everything here, this is different from this carbon here. So this carbon and this carbon is different. This carbon and this carbon is the same. They will appear the same signal due to symmetry. So I'm just highlighting the different carbons. So I have 1, 2, 3, 4, 5, 6. I have 6 times different carbon environment. Looking at these, I'm looking for 6 peaks in carbon NMR. So this must be isomer number 4. Okay, because it's got 6 peaks in the NMR, so this must be isomer number 4 there. See if that's better. Nope. So that line there can't be reversed. Oh no, I don't want that. I don't want the whole thing to be erased. Nope, I don't want that. Okay, that's much better. See if I can erase that. Okay, much better there. I should probably try and work on a okay, maybe I'll include in 1, 2, 3, 4, 5, 6. So 6 different carbon there. Okay, that way I don't have to erase for the rest. There's a mirror plane, but the mirror plane for this one is around there, meaning to say this carbon is the same as that carbon, this carbon is the same as that carbon, and then this carbon here is the same as that, and that carbon there is the same as this because of the mirror plane down in the middle. So 1, 2, 3, and 4. This is 4 times different carbons. And looking at the 4 peaks in the carbon NMR, so this must be isomer 2. Okay. Now I can't be bothered to erase that now. In terms of the mirror plane for the other one here, so it's there. So this thing is different from here because here you're next to something that is CH3. Here you have next to something which is just hydrogen. But this carbon here is the same as that due to symmetry. This and this is the same due to symmetry. This and this is the same due to symmetry. Oops, not pink but green. 1, 2, 3, 4, 5. So 5 times different carbons. So there's just isomer 3 there, leaving us with isomer 1 for the other one because this one is the most symmetrical of all. If you think about that, and if you think about through the middle here, this and this, so altogether you have 1 and 2 and 3 because these and these are the same, these and these are the same, these and these and these and these are the same. So 1, 2, 3 environment. So altogether you just have 3 times different carbons environment, which is why this is going to be isomer 1 there. Okay, so I hope that makes sense for your 4 marks. Part B, so this is question 6, part B. So it looks like a synthesis question. You start from a benzene ring, not a problem. You have chlorine and then CH2, 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 and then COOH. So double check ClCH2, 3 of them, and then CO2H. And you have it in the presence of AlCO3. This is your step 1. This is actually going to be a reaction, a name reaction. This is called Friedel-Crafts alkylation. That is the name of the reaction. It's not the type of reaction. Be very careful. The type of reaction is stated in the AS. The type of reaction is going to be substitution. And the mechanism, as stated in A2, is electrophilic substitution. I think a lot of students are confused when they think they know the name of the reaction. They thought it's the name of the mechanism or the type of reaction, which is entirely wrong. So what happened with the AlCO3 and the Cl is this and this will form AlCl4 minus, and then you get a plus on the electrophile such that you will get a plus there, and you will chop off this bit. So you get 1, 2, 3. So CH2, 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 and then a carboxylic acid there. Okay, so this must be W. If you double check, CH2, 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 and then the CO2H at the end there. Obviously then, what does that form? That gives you the acyl chloride. So if I just copy this, which means I don't have to redraw it, and then I convert the carboxylic acid at the end there to become acyl chloride. So this is basically using SOCl2, or you can use PCl5, or you can use PCl3Cl2. Those are your common reagents to convert carboxylic acid into acyl chloride. So that is your step 2 there, whereas previously that was your step 1 above. Okay. Obviously I run out of space now, so what I'm going to do is I will just copy all of these onto the next page. Nope, I don't want to copy, I want to cut it. And I'll just start afresh from here with a little bit more space so I can work down. And what I have in step 3, in step 3, I just add AlCl3 because then I have acyl chloride which will react with AlCl3 to give you acyl cation, because that, on the other hand, just now we have Friedel-Crafts alkylation for step 1. For step 2, what we have is we have Friedel-Crafts acylation. So Friedel-Crafts is the name of the, I think it was a duo who actually discovered this particular reaction. The type of reactions is still substitution. You are doing substitution on a benzene ring, and the mechanism is going to follow electrophilic substitution. So all of these things are basically in the syllabus as part of electrophilic substitution. So what's going to be my product? I'm going to get Actually, what I can do is I can just paste this. Oh no, I don't want that. So what I'm gonna get is actually the benzene ring like that, and then I have a plus. What happens is the benzene ring can attack that and loop onto itself. So what I have is 1, 2, 3. So I have just drawn part mechanism there. They are not asking for mechanism, they are just asking for the final product. There's a hydrogen there that you can kick out, and you kick out H plus, which will combine with the Cl minus that get released from the AlCl4 minus, such that you get plus HCl. But what will happen is 1, 2, 3, and then the fourth one goes there, and you will have another CO like that. So this is 1, 2, 3, and 4. This is going to be your final product. So I don't need okay, maybe I can put that on the side so that you can see what's going on, but that is obviously not what is required. What is required is your final answer, and that is the structure of X. X is equal to, well, they put in a bracket, X is C10 H10O. Be very, very careful. It is not another benzene ring. It's just another ring, but it hasn't got a benzene in it. And there are 6 carbons, 7, 8, 9, and 10. And there is 1, 2, 3, 4 hydrogen, 5, 6, 7, 8, 9, and 10 hydrogen, and 1 oxygen. So there's compound X there. Speaking of what I've done there, I talk about Friedel-Crafts alkylation. You will form AlCl4 minus and an alkyl cation. You will form AlCl4 minus and you get an acyl cation. So a difference between alkylation and acylation is kind of summarized in the next bit of the question. So this is B part 1. Write an equation for the formation of the electrophile. So you're going to use RCl plus AlCl3. What will happen is you're going to get R plus and you get AlCl4 minus. What happened at the end of the electrophilic substitution is a catalyst. So what happened is the H plus that you kick out plus the AlCl4 minus will then regenerate the AlCl3 catalyst, and that is regenerated or reformed because the catalyst is not used up in the reaction, and you get steamy white film, which of course is given out in the reaction. So all in all, I just will eliminate that equation because it's not being asked here. Deduce and draw the structure. That is done. And then number 3, suggest the reagent and condition for step 2. Step 2 was basically converting the carboxylic acid into acyl chloride. It's in the A2 acyl chloride topic. We can use SOCl2, PCl5. I'll just stick with SOCl2, but of course PCl5 will work. What is interesting is they also want the condition. So you gotta say the condition and not just the reactant, and you do this reaction at room temperature because they are very, very exothermic. In terms of the equation, so these are the extra thing from AS. When you have ROH, when you have SOCl2, the ROH will get converted to RCl. You will kick out SO2, you will kick out HCl. So you can imagine when you have carboxylic acid, you're going to do the exact same thing with the OH. Then you're going to get acyl chloride, which is RCOCl, and you will also kick out SO2, and you will also kick out HCl as well. So you see they are very, very similar. One thing you have learned in AS, and the other thing is A2, but in an A2 setting, they can ask you anything from AS in A2 paper because it's within their right to. The next question, part 4, is basically asking you to do the mechanism. This is the electrophile formed in B part 1. We are still using R plus that we already formed in the previous equation. So we start off from the benzene. You will know from my previous tutorials that instead of using the delocalized structure, I like to use the cool structure where I show the alternating double bond. But it does not mean that I don't know how to use this. I do. Instead of from the double bond, I use the electrons in the benzene ring, attack the carbocations. We know that this is the slow step because this is rate determining step. As you lose aromaticity Aromaticity is the stabilizing effect in a benzene ring. So when you lose it, it's always going to be slow. It's always going to take a lot of energy, very high activation energy. So if my R is there and I have a H there, I have a plus there. That is typically what I would do if I have alternating double bond like this. But here, I am trying to use the delocalized form. So what happened is this plus charge could get delocalized throughout, because this is actually a carbocation, a carbon with 3 bond pair and 0 lone pair. So this is sp2, 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 sp2. These are all planar. So essentially your charge could be delocalized over the carbon sp2, which are planar, but not on here, because this is now 109 degree carbon sp3 tetrahedral. So not only I can draw what I normally draw, I can also do what usually is shown in marking scheme. So I don't have to always follow one thing. I can do many things actually, but I do know what I'm doing, so that I'm not easily tricked or anything. What happens is I want to return to being aromatic, so I will lose the H and it will get the electrons from the CH bond. Both the electrons go back into the ring. Whereas for my other form, where I show using double bond like this, from my double bonds, from my CH bond, the electrons go back to give me the double bond there. The alternating double bond is basically not the correct structure. The correct structure is the electrons get delocalized to give you that benzene ring. And then this is minus H plus. This is going to be fast with low activation energy, because you are restore aromaticity. You are restoring the stabilization due to being aromatic. And that's when you will kick out the H plus, which will take away the Cl minus, the AlCl4 minus that was formed from the catalyst, will react with the H plus to give you AlCl3 catalyst that will reform, because the catalyst is not used up in the reaction, and in the overall reaction you produce HCl as another product, steamy white film. Okay, draw the structure of the intermediate. So they do want you to draw the structure of the intermediate. Make sure it's a carbocation on that carbon there, and you want to restore the aromaticity and not do addition reaction. Instead, it's an overall substitution of this hydrogen on the benzene with this R group. That's the end of the 11 mark aromatic chemistry.